Hello, everybody. Yeah, so last time we talked a little bit about a ring buffer, and we used a link transfer queue to compare the to our ring buffer implementation to see if it really had any sort of the speed. So typically, when you're using a ring buffer or a circular a queue, if you will, a circular buffer, you're looking for basically a lock-free way to communicate between threads. So last week we reduced a lot of the locks by using atomic references, but still we were only 66% faster. So this week we're going to kind of pick up and look at that. A little bit about my background. I've taught and written many courses: Struts, Scala, Java, Spark, Cassandra, Kafka, Spring, Hibernate, JPA. Also wrote a few books, one on Java tools for extreme programming. I was a 2018 Java champion. I've contributed to multiple open source projects, including a very fast JSON parser and some high-speed in-memory communication type stuff. And I work on both engineering management consulting, and I do low-level high-speed compute consulting. So yeah, that's kind of my background. I used to travel about 20 weeks a year doing training for a few years. I enjoyed training, but now it's basically most of that's gone online, and I'm trying to get up to speed on creating videos and getting used to using the video editing software, setting up a microphone, and trying to get a decent environment going. So that's a little bit about what I'm trying to do. Just learn the tool set, and toying with the idea of a video blog, or a vlog, I guess it's called, or a writing some courseware, maybe publishing that courseware somewhere. But right now, just getting used to the tools, and I want to get into a regular habit of producing said tools, said videos, and just kind of get used to it, and eventually branch out into creating courseware, because I enjoy creating courseware. The last course I wrote was in 2016. I wrote a course on Kafka, 2016-2017, which I taught a bunch of times, and also taught some courses on Cassandra and Spark in about the 2017-2018 time frame. So yeah, this is not perfect. I went and got a microphone. I needed a microphone. You can see right here is the microphone. Well, you can't see it but you will see it later. I doing a little more prep on the outline, the meeting notes. I'm trying to kind of perfect the process. It's not going to be perfect when I create the first. This is only the second video. So, and then it's a matter of what's next. So we're going to cover how we got that speed improvement for the ring buffer, how we were able to improve the speed. So now it's 3.6 times faster than using a link transfer queue. Versus 66% faster. So we'll go into how we did that. And we have got other topics: Bloom filters, dynamic programming, Java concurrency, all little projects, side projects I worked on this year. Index overlay parsers, base 62 encoding. That was a cool project. Implemented it in like 8 or 9 different languages, including Clojure, JavaScript, TypeScript, Java, Swift, maybe Rust, and a few others. So that was a fun project to work on. And so if that's from that list, if there's something that you particularly want to see, otherwise I'll just kind of go in whatever order I feel like. So let me know, give me some feedback. Also, I'd like to maybe do some talks on some more managerial engineering management, engineering software development type things as well, and maybe just some tech reviews. So without further ado, let's get into the improved ring buffer and how we did it. All right, so last time we talked a little bit about the ring buffer, and I'd like to continue that discussion. So again, just for comparison, I did a link transfer queue. I've got 2 threads. One's a writer thread, one's a reader thread. I wanted to get a baseline of what that would be. And then I wrote a ring buffer, and I have another test that looks almost identical, but it uses the ring buffer instead of the LinkedTransferQueue. And then I have another one where I have an optimized ring buffer. And let's just take a look at these real quick. I went into the coding for the ring buffer the last time. And I'll talk a little bit about the what optimizations were made for the ring buffer 2. So let's just look at the timing. So this is the queue, the built-in queue in Java concurrent lib. Let's just run that real quick and see what the time is, what the timing is for it to do 30 million messages. So that's 30 million sends and 30 million receives, really just timing the receive count. Well, kind of both, but mostly focused on the receive count. So in 3.4 seconds, it goes down to 3 seconds usually. Let's see if we can get it there. 3, yeah, so it's pretty close to 3 that time. Now, compared to the ring buffer, when we run this against the ring buffer, so that was 3 seconds and a little change. This should be about 2 seconds and a little change. Well, a little bit lower than it usually is. I did fix some things last night. Oh, now it went up. So 1.9, 2.6. Let's run it one more time. And 2 seconds. So around there. Of course, we could do a warm it up a few times and then run it. There's ways to improve the perf testing. This is just kind of a starter thing here. But here's the same test. This is though for the optimized ring buffer. We'll talk about what the optimization is in a second here. So let's run this. And here we go. We're running it. And look at that. 868. So under a second. So half the time of the ring buffer, which was 2/3 the time of the first one, and 3.2 seconds versus 868. So we have, let me just see what that is, 868. So it's about a 360% improvement, thereabouts. That's pretty good. Now, what did we do? And it's double the speed of the ring buffer that the first one we wrote, and it's 3 times the speed plus 3.6 times the speed of the other. So more than double the first ring buffer, and almost 3.5 the transfer queue. So what did we do in this ring buffer to make it so fast? Well, it's what we don't do that makes it faster. So we added this idea of a read count and a write count. And what these are doing is periodically we will calculate the distance from the reads to the writes and from the writes to the reads. Now remember that the reads have to be behind the writes. So let's say that the reads are 200 behind the writes. So that we'd set the read count to 199, and then as periodically, or as we go to 0, definitely as we go to 0, we'll recalculate the read count. And what that means is these atomic references that we have, remember we had this location that stores a ring number and an index, and then we store those locations for the write location and the read location in this atomic reference. Well, that atomic reference now doesn't have to be accessed except when we run out of the counts. So we calculate the distance to the read or the write, and then we only update the atomic reference if our count is 0, or just periodically. I'll show you. So here's the write object. It looks just like the write object from before. I'm going to close this. Looks like just like the write object from before. So here's the read location. We're getting the read ring number and the read index. Then we have this new method called calculate write distance. So if the write count is 0, that means we don't have any more writes. So we're going to calculate the distance between the read and the write. Remember, we can't be more than 1 ring ahead of the read, otherwise we're writing over the read's locations. So we need to calculate what that distance is, and then as long as the count is greater than 0, we just write. So we never have to synchronize. So if we are 500, if the write count is 500, for the next 500 times write is called, it will not synchronize. Now, two things that we do here. This is the similar as before, right? Here, if periodically, and periodically I just said every 100 writes, we're going to go ahead and sync. So we'll sync when the write gets updated, but we'll also sync when periodically every 100. So when the write count goes to 0 or every 100, we'll do a sync write. This is basically a sync write right here. That's the same code as a sync write. So sync write is basically just storing the write ring number and the write index into the write location, the writer location. Okay, so then we have our read. But before that, let's look at the calculate write distance. So this is basically calculating the distance until we run out of space to write, right? So if we're on the same ring number as the read ring number, so if the write ring number is equal to the read ring number, then it's just the ring length minus the write index plus the read index is the count. Okay, so if the write ring number is 1 ahead of the read ring number, sorry, I had to think about that, then it's just the read index minus the write index. And then we have the similar thing to calculate the read distance. So for the read operation, we do a read. If the read is less than 0, we're going to read that write location. We're going to calculate the read count. Otherwise, we're going to keep accessing the reads as long as the read count is over 0. So if it's under 0 or equal to 0, then we do this block. Otherwise, we just read that location. And then this block is just like it was in the last video. So recommend that you read that one. Okay, so that's basically the optimization. So we're not synchronizing as much. We're either synchronizing every 100 or the distance between the read and the write location. And that's what gives us that extra speed. All right, so here's the atomic reference we talked about last week. Or not last week, the last thing that we mentioned that we'd bring it up again. So this basically allows accessing a field atomically, which means the low-level CPU compare set operations. I really recommend reading up on var handle and the API docs for atomic reference and for atomic int and just for atomic variables in general. There's also a nice write-up in the Java tutorial from Oracle. Gives a little example here. This is a counter that's not thread safe. This is one that's using synchronized blocks, and this is one that's using an atomic integer. And if you want to know more about the difference between those, I recommend reading up on synchronization, thread interference, memory consistency errors, synchronized methods, intrinsic locks, and atomic access. And that should give you the background with the atomic variables and some of these other constructs that we're using. But I highly recommend, if you're not familiar with those, take 5-10 minutes and read through that. I think it's going to, if you're an old Java dog, and then it's going to help you understand things a little better. And if you're newer, it'll give you a leg up. So try it out. All right, that's the second video as a wrap. So, next week we'll probably cover Bloom filters. If you want me to cover more of the Java concurrency libs or go into more details about atomic variables versus references or any of the built-in concurrency, let me know. There's a lot of subjects. I said, like, I wrote an index overlay parser. I rewrote it recently. Could talk about that. I have a service mesh talk I gave at CTO Forum in 2019. It could resurrect that, or actually it was 2020 before the things got too crazy. I got an accelerate development talk, which we could cover as well. That's more engineering management, DevOps sort of talk, but it would be, I think, a good one. And yeah, so let me know. It's been fun. See ya. Tune in.